The HTML structure is minimal, consisting of a single figure element that contains a canvas, which serves as the sole rendering surface for the entire animation. The CSS applies a universal bodybox model and uses viewport units and flexbox to make the body and figure container fill the entire screen. The figure is given a midnight blue background, and the canvas is absolutely positioned within it to ensure it matches the container's dimensions exactly. This creates a full screen contained drawing area with no surrounding margins or paddings. The JavaScript is the core of the application, managing the entire simulation through a single GameObj class and a recursive animation loop. The GameObj class uses a type-based system to define three distinct entities: a target ship that moves and bounces off walls, rockets that calculate intercept courses using trigonometry and spawn visual trails, and the trails themselves that fade out over time. The animation loop drives the simulation by calculating the time elapsed between frames, updating the state and position of every object, and then rendering them to the canvas. This structure creates a self-contained world where the objects interact based on mathematical calculations for movement, collision, and lifespan, making the canvas a dynamic and animated scene. Alright, let's dive under the hood and see how this thing actually works. I'm gonna walk you through each major part of the code, piece by piece. GameObj rotation direction function is a static method, determines the shortest rotation direction, -1 for clockwise, 1 for counterclockwise, 0 for no rotation, needed to turn from the current angle to the target angle. How it works? It calculates the raw differences between the angles, then normalizes it to the range -pp by adding or subtracting 2p if the difference exceeds those bounds. This ensures the calculation always finds the shortest path around the unit circle. Why it matters? It is critical for the rocket's homing behavior, enabling it to turn smoothly and efficiently towards its target without unnecessary full rotation, which is key for realistic and performant pursuit simulation. GameObj update. These methods update the state of each game object based on the elapsed time, t, handling movement, collision, and lifecycle management. Using a switch statement, it executes type-specific logic. The target ship moves and bounces off walls by reversing its velocity. The rocket calculates the angle to the target, adjusts its rotation incrementally, moves forward and spawns trail particles at intervals. It also checks for collision and removes itself upon impact. Trail particles move, grow, age, and fade out. They self-delete when their lifespan ends. It decouples state evolution from rendering, ensuring all movement is time-based for consistency across different frame rates. The collision detection and particle aging are essential for gameplay feel and visual effects. GameObj render function. This method draws the object to the canvas based on its current state and type. For ships and rockets, it uses canvas transformations, translate, rotate, to position and orient the emoji text. The rocket's rotation is offset by p divided by 4 to align the emoji with its direction. For trails, it draws a colored circle with transparency that decreases with age. It separates rendering from logic, maintaining clean code structure. The use of transformation simplifies the drawing of rotated objects. and the HSLR color model allows easy manipulation of hue and transparency for vibrant fading trails. Animate function. This is the main animation loop that drives the entire simulation, called recursively to update and render each frame. It calculates the time elapsed since the last frame, clears the canvas, then iterates through all objects in-game OBJs, calling the update and render methods. It then requests the next animation frame. It creates a smooth, continuous animation. The use of elapsed time ensures all motions is independent of frame rate, providing consistent behavior on different hardware. The functions work in concert. Animate manages the loop, update changes object states, and render draws them. The rotation direction method enables intelligent navigation, which is the core of the rocket's behavior. The time-based updates and canvas transformations are fundamental to creating a polished and responsive animation. This structure demonstrates a classic game loop pattern, and expanding it would involve adding more interactions or refining the physics and rendering. The link to the file location is in the description. Let's scan the implementation. That's all from my side. Be well.